Good afternoon. I'm Sumanta Pattanaik. I'm an associate professor in the Department of Computer Science at UCF. After receiving my Ph.D. in 1993, I spent a couple of years in Real Lab in France. 6 years following that, I worked at the program of computer graphics of Cornell University. I joined UCF in 2001. My expertise is in the field of computer graphics and visualization. So here at UCF, I mostly teach computer graphics and data visualization. So the courses I've listed here, many of them I teach now, and most of the courses I have developed or revised at UCF. Okay. I have co-authored a couple of books. One of the textbook in the computer graphics, the second edition of this one will be out this fall. Okay. So last fall, when I was faced with the problem of remote teaching of our large undergraduate graphics class, about 150 or so, so that my graphics class relied heavily on face-to-face teaching with extensive use of whiteboard and hands-on graphics programming. So to teach this course, I had to devise a novel teaching aid to provide similar experience to the students remotely, and it worked. So it involved creating close to 40 online interactive workbooks, actually, so that they can interact, they can see while teaching or after teaching as well. So this technique not only works good for remote teaching, it also, I find it useful for face-to-face teaching. So I wrote up my experience for the benefit of computer graphics community and submitted to Eurographics, and we are going to present this one early next month. Okay, so I have published about 100 plus papers in peer-reviewed journals and conferences that have about 8,000 or more citations. I have served as an editor in SEM Computer Reviews, the graphics part of that, and I have chaired a graphics rendering symposium. I currently am serving as a co-editor of a special issue of an international journal. The special issue is on big data visualization. I'll tell you at the end, though it's still open for submission if you're interested. At UCF, I got about 900K of grant money, and I graduated 7 doctoral students and a few master students. So I'll now give you a preview of some of the work I have carried out at UCF. As I told you, my area is realistic rendering. So I first, in the beginning, from the beginning, my focus has been on creating realistic rendering. So this work I'm showing you is my early work on realistic nature rendering, okay, in real time. That means realism and rendering speed of complex scenes was of prime importance there. So the image plates you see here show the rendering of unlimited number of grass blades on a large grassy terrain or in a football field. Okay, so here the important part is showing the details of the individual blades when required. So when you zoomed in, and complete with lighting and shadows on each other on the terrain also was important to realism. Okay. The image plate you see at the bottom, actually I'm showing the rendering of trees complete with leaves. Actually, it's not the rendering of trees that was important. It is actually the accurate lighting part that was important or difficult. So what is the lighting part? It involved transmission and scattering of sun and sky inside these trees, inside these hundreds and thousands of leaves. Okay, and they created certain appearance that was important to reproduce. Okay, so our focus here was on mathematical modeling and real-time and providing real-time solution. This work was sponsored by Electronic Arts. It led to a number of publications, and this work was later actually adapted into many game engines. On this slide, I show some of work on real-time simulation of lighting phenomena. So here you see caustics on water. The caustics, normally you see the light goes and you see that type of appearances below. And also you see this dispersion of white light into wavelengths and interaction of light on translucent material, which actually gives the soft appearance of objects, for example, marble or many organic objects. So here the simulation of that one I'm showing. On the bottom plate, I saw the transport of light in a media containing dust and smoke. Okay, quite often it's possible, the smoke here and the dusty room. So if you want to accurately reproduce this, you have to actually go back to the light transport equation. But if you want to provide a real-time solution, then you have to make some simplification with still preserving the actual accuracy and visual accuracy I'm talking about. Okay. And so, so the emphasis was on data structure and algorithms, and so that you can get the results, visual, high-quality results. And this work was published in leading conferences and journals are listed here. On this slide, I show some of our work on real-time rendering of huge urban terrains. Okay. So the emphasis was scale-accurate reproduction, so that you can overlay satellite images on the rendered images at any scale you want to. Okay. And so then it can be used for decision making, such as line of sight calculation, such as pathfinding in a complex evacuation situation. I'm talking about this type of requirement because this work was actually carried out for several military-related projects. Okay. So again, the emphasis was actually developing algorithms and data structures so that we can provide accurate rendering at sustained frame rate. That was of prime importance to them, okay, to the sponsors. So on this here, I show my work on simulation of polarized light transport. So this was sponsored by NSF, and the project was actually for accurate modeling of material reflection from non-metallic surfaces. Okay, most of the real-world material we see around us are actually non-metallic. Okay, a major component when you say reflection from those material, actual reflection comes from the interaction of light under the surface. You see here, light enters inside, interacts with these tiny pigments there, and then this, and then comes out as reflection. So and physics researchers will know that polarization of light plays an important role in reflection, refraction, and polarized scattering with the pigments. So for this work, we also worked on polarized light transport and then a solution of that one. So as a byproduct of this work, we developed a polarized light transport solver. We have a polarized ray tracer and a tool for modeling reflection property of material composed using user-defined pigments, because user can define, and if the physical properties we can specify, and then our system can find out its a material property. We generally, polarized light is not visible to the human eye, so we developed a scheme for visualization of this polarized light. So because we are carrying out polarized rendering, so we extended an image format, existing image format, PNG format, if people are aware of. We extended that to for the storage, transmission, and visualization of polarized images. That means every pixel had color and also polarization information. This work also led to a collaboration with University of Arizona team, to work on a related DARPA project. So then here I show our work on medical volume rendering. So here, medical images, as you know, they provide considerable amount of anatomical information and facilitate medical practitioner for performing effective disease diagnosis and deciding on the best course of surgery and treatment. So a transition from these grayscale images, grayscale CT scan or X-ray or MRI images to colored 3D representation with anatomical structures actually enhances the capability of medical professionals in extracting valuable medical information. So we developed tools for interactive visualization of volumetric data, but most important is our emphasis was on visualizing on mobile devices the large volume data. So our effort was towards development efficient data representation and working to a good client-server architecture so you can cater to as many mobile devices connected to the server and still providing interactive rendering of this medical volume, probably to the surgeon at the right time, maybe at the time of surgery. Okay. So we also developed interface for assigning optical properties because the color and all that has to be assigned, the information has to be assigned. So that's called a transfer function. So that one user has to specify that one. So we developed an interface for that one as well. So this optical property assignment to the volumetric data is important because it doesn't have, you see, started with a grayscale image. But this assignment requires human expertise and interactive creation of transfer functions. So that could be also it's time consuming. It also could be erroneous. So this last year, we worked on developing an automatic color transformation method by finding actually a deep semantic correspondence between some data reference image and these medical images. For the reference image, we actually used visible human data that is publicly available from NIH. And so basically, as you understand, it's a deep transfer. So that means deep learning is involved to some extent. And so as a reference image data set, but this data set that we use from NIH is still limited.
Second, third guy.
Sorry? It's only limited, so we developed an effective reference image recommendation system to aid the selection of suitable images for reference from the reference image set. Okay, so our algorithm successfully performs color medical volume visualization and essentially eliminates the process of user interaction for a transfer function creation. So this is, you see here, this particular work was published last year in a conference. So finally, I showcase our recent work towards incorporating wave nature of light into realistic rendering. Most of the algorithms in image rendering today use a ray nature of light. However, certain phenomena of light that can only be reproduced by simulating wave characteristics. On the top, I'm showing some work on a thin film rendering. Thin film is putting thin film is actually a common practice to modify material appearance. In optics, for example, coating is often used on mirrors or lenses to modify the reflectance and transmittance properties. So these changes in reflection and transmission property are due to the interference of the light waves. Somewhere constructive interference and destructive interference. This is well known, but bringing them into rendering is actually a little bit of challenging. So last year we published a paper on CGI and working on this one. So the work was on anti-reflection coating rendering. Here you see without anti-reflection coating, and you start adding different layers. Not a single layer doesn't work quite often, so you have to work multiple layers, and how it reduces the reflection. And we show here in a rendering of a car, this window, and you see here there is without coating and with coating. So this work, as I told you, it was published in CGI, and we have real-time renderings available on the web page as well for the community. Okay, so now we just worked on a hair rendering algorithm, which just submitted to Aerographic Rendering Symposium. I think it would be surprising to many. Realistic hair rendering is very complex and computationally demanding task. So the reason is average human head has about 100,000 hairs, but the hair thickness is about 60 to 80 micrometers. Each hair is actually modeled is an elliptical cylinder. Okay, so this hair, if you want to realistically simulate the hair, render the hair, it requires complex calculation of interreflection, scattering of light, and diffraction, which is basically wave nature, requires wave nature of light. So most of the other things like reflection and scattering can be simulated by ray tracing. However, the diffraction effects require the wave propagation. But if you want to carry out the wave propagation with these 100,000 or more hair strands, it does take actually several days for this computation, even at this time. So that is very difficult to use in practice. So what we have done is developed a dual hair scattering model. So basically, it utilizes a combination of ray tracing and wave transport model. Okay, so ray tracing used for whatever it's best known for, so like scattering, reflection, and all. And so we fall back to wave simulation only when the effect is deemed significant. For example, here you see this is an actual photograph, and we try to simulate this particular effect, which is basically a diffraction of hair. And of course, all the rendering and all that fun is possible. So at this moment, the interesting aspect of this paper, this addition of this particular effect hardly adds very little extra cost over the current state of art rendering time, whatever time it takes currently. So we compare that, and so the addition is only very little. So let me talk about my current interest. Of course, I'll continue working on this area, of realistic rendering and visualization. Okay, but I'm listing here some of the work I wish to carry out. So I want to apply deep learning to rendering problems. I'm late in actually adapting deep learning into my graphics algorithms. I've just started, as I told you, a little bit in visualization, medical data visualization. I wish to expand on this one. I used to continue adding wave simulation to rendering as and when the quality demands, because some simulation of wave nature is expensive, but depending on when it required, and I certainly like to work. So I wish to basically, I want to continue this wave rendering work as well, but in addition, the experience gained from my rendering work, I want to bring to simulate sound wave propagation. It has got its application as well. Okay. I want to expand my data visualization research by working in collaboration with groups that particularly handle big data. In fact, I'll be happy to collaborate with any group in the audience that can benefit from my rendering and visualization experience. Okay. I want to thank some of my students whose work I have showcased here, and also to my collaborators, external and UCF collaborators who participated in some of the work I shown here. I thank my industry sponsor and my federal sponsor. I take this opportunity to tell you that this special issue deadline is first week of May. So if you are interested in submitting anything, please do submit to this paper. It's on big data visualization. Thank you.